Okay, so welcome everyone for this new SIPTA seminar of October. As for those of you that do not know these seminars, I just remind you that these are seminars about IP and connected topics. So this is the case today because we will have a talk connecting game theory with lower probabilities given by Milan Studeny. But this day, Kike will Enrique Miranda will chair the session, so I will let him introduce the work of Milan in more details, and then Milan will tell us everything about the cone of exact games. So, Kike.
Okay, thank you, Seb. So it is our pleasure and my pleasure today to chair the talk of Milan Studeny. As many of you know him, he's coming from the Czech Academy of Sciences, and he has been working on quite a number of topics, some of them more related to imprecise probabilities, some of them connected, but maybe not so directly. He has been doing a lot of interesting work on the marginal problem, also on conditional independence, on probabilistic knowledge-based systems, on information theory, and on the topic that he's going to talk about today, which is game theory. He has, well, about 50 journal publications, a monograph on probabilistic conditional independence. And as Sebastian was saying before, one of our goals with these seminars is to explore the connections between imprecise probabilities and other areas, because, well, many times there are many results that are like discovered independently and quite much closer connections than sometimes we are aware of. And I think this is the case today, so it is very nice that we can hear from Milan Studeny to explore in more detail these connections between game theory and imprecise probabilities. So, if you're ready, Milan, well, the floor is yours, and thank you very much for giving the talk.
Again, thank you for nice introduction and for inviting me and giving a possibility to give a talk here. The title of my talk is a combinatorial description of facets of the cone of exact games or coherent lower probabilities. And it's presenting a joint work with my colleague Vaclav Kratochvil in the Institute. So this is kind of summary of the talk. So I will, in the beginning, I will repeat the abstract. After that, I will define what are collisional games and mention so-called balanced and exact games. And after that, I will try to make some relation to the theory of imprecise properties to the concepts of lower probabilities, avoiding sure loss, or coherent lower probabilities. Then I will present some classical results in game theory from 1960s by Shapley about the cone of so-called balanced games. In analogy to that, I will then present some later relatively recent results on the cone of exact games. Point is that one wants to describe facet-defining inequalities of these cones. What is, say, our contribution besides the result is that we proposed certain diagrams, pictorial diagrams, representing that inequalities. Then I will present the combinatorial solution of that problem, how to recognize facet-defining inequality. This leads to the concept of indecomposable main semi-balanced set system. I will also try to say you something about some hidden symmetry in the facet-defining inequalities for that system. And I will try to end with some remarks on some close related results. Okay, so the abstract. So first, the concept of an exact transferable utility coalitional game was introduced in 1972 by Schmeidler, and it appears that it corresponds to the concept of coherent lower probability, studied in the concept of imprecise probabilities. So here I give a reference to the Schmeidler's paper and the book by Peter Wally. In our recent paper, we characterize the facets of the cone of exact games, which basically means we characterize minimal set of linear inequalities defining that cone. In a certain way, this result offers, at least on the theoretical level, some linear computational test to decide whether a given lower probability is coherent or not. What's the point is that these facet-defining inequalities appear to have combinatorial interpretation. So they correspond to certain, say, set systems, that means systems of collision, or formulated in context of imprecise probabilities, subsets of the sample space. But certain special set systems which have some internal nice combinatorial structure. So this talk is about that result from 2022 paper, where we characterize these set systems, which corresponds to facet-defining inequalities for the exact cone, as the so-called indecomposable main semi-balanced systems. Point is that these semi-balanced systems are actually generalizations of the concept of balanced system, which was brought into existence already by Shapley in 1960s. And as I said, we introduced that pictorial representatives, and I will try to show them by means of some web page created by Vašek. And they describe all the facet-defining inequalities for the case when the sample space has cardinality at most 6. So let me start with some basic definitions. So throughout the talk, N will denote some non-empty finite basic set of variables. And in game theory concepts, the elements of this basic set correspond to players, and subsets of that set N to coalitions. P of N will denote the power set of N, that means collection of all subsets of N. This symbol Rn will be used to denote the Euclidean space of real vectors whose components are indexed by elements of N. Okay, so-called transferable utility coalitional game over N, it's modeled by a real function on the power set of N, such that value for the empty set is 0. And that function is sometimes called the characteristic function of the game. And the game is called then non-negative if these values are non-negative. It's standardized if the values for the singletons are 0. And normalized is value for N, which is sometimes in game theoretical concept called grand coalition. It's 1. Here is the definition of a core polytope, which is crucial concept in this context, in context of coalitional games. That's a polyhedron in Rn, consisting of those vectors in Rn, such that some of the components in I equals to the value of the grand coalition, and for any coalition, the sum of components in A is bounded from below by the value of the coalition. Here I present something which is called profit interpretation of the core polytope. In this, implicitly assume that M is non-negative game. So the value for the grand coalition is then interpreted as the amount of money, say the players altogether won. So they bet a lottery, get a won, and now they wish to divide the money they get. So the value for a coalition A, it's interpreted as the strength of a coalition. So if the total win is divided among the individual players, then members of any coalition should together obtain at least what is the strength of the coalition. So the vectors in this core polytope are interpreted as a payoff vectors. compatible with the possible basic requirements dictated by the strength of the coalitions. Here is some simple illustration of that concept. So we have three players, ABC, and this table shows you this function, this characteristic function of the game. So the game, it's game value for empty set is 0. It's also non-negative, you see. It's standardized values for singletons are zeros, and it's also normalized. So in this particular case, because elements of this core polytope belong to plane specified by this xi plus xb plus xv equal to 1. So, we also can observe, so it's a two-dimensional polytope, therefore. And this inequality xb plus xc is bounded from below by value for bc. It's actually the same like the value for xa. It's bounded from above by 1y minus values for of the coalition for bc. So for this reason, this is the right rewriting of that core polytope. So as I said, here is a kind of picture. You see that core polytope, it's a subset of that so-called probability simplex. And for example, the inequality for xi means that the core it's belongs to some band between two lines. This line describes the set where xi is equal to 0. This line extended describes the line where the xi equals to 1/2. So in between of them must be the core. So the same is done, same consideration is some for xb and xc, and you get that core is actually this triangle. So core in this case has exactly 3 vertices. A game is called balanced if the core is non-empty. By the way, this definition of balance, it's motivated by a result. I will present the Shapley results characterization of the condition by means so-called balance condition. The original terminology, I think, was weak or something like that. Game is called exact if for any coalition there exists element of the core which is tied for that element. That means for which that lower bound is attained. It is immediately from the definition that every exact game is balanced. And one can also observe that a non-negative exact game is monotone, which means this. Why it is so? It is because exact game must be super additive. That means if we have disjoint SNT, value for their union dominate some of the values for their parts. To see this, consider an element of the core, which is tied for S union T. And then this part certainly nominates the values for C. This part nominates the value for T, and altogether we get exactly super additivity. Here is another example of a core polytope. This time we had 4 players, and the game is described here, this characteristic function. And this polytope, if you have 4 players, it's actually 3-dimensional because it lies in that hyperplane specified by this restriction. So in this, here is a picture how it looks like. In this case, the polytope has 4 vertices and also is specified by 4 inequalities. Okay, let me come back to lower probability. So in context of imprecise probabilities, basic set is interpreted as a sample space for the considered random variables. All it is called frame of discernment in context of Dempsey-Schaeffer theory of evidence. What I will present now in this slide and the next page, it's actually taken over from October 2022 SIPTA seminar presentation by Ignacio Montes, called Colatitional game theory versus imprecise probability, two sides of the same coin, where they make some dictionary between these two mathematical theories. So, Blau probability is a function on the power set of n to interval 0, 1, such that value for empty set is 0, value for whole sample set is 1, and which is monotone. So therefore, if I simply take on a place, say, underlined p, this function m, this characteristic function of m, then you see immediately that lower probability is nothing but normalized monotone game over n. And having in mind the previous observation that non-negative exact game is monotone, we see that normalized non-negative exact games is a low probability. And there are other concepts there in imprecise probabilities, and this is concept of cradle set and coherent lower probability. So cradle set is collection of all probability measures which somehow dominate the lower probability in this sense. So then one says that lower probability avoids sure loss if it has non-empty cradle set. And we say that it's coherent if for any event A, there is a probability in the cradle set for which the lower probability is attained. Therefore, given a normalized monotone game, that is the game which corresponds to lower probability, we can interpret it any vector in the core polytope as a probability distribution. Yeah, value of probability of an event is sum of components of that vector. And then you see immediately that actually core polytope is basically the same like cradle set. M is balanced game if and only if the probability avoids sure loss, the low probability, and it's exact game if and only if it is coherent lower probability. And also we see that actually in terms of exact games, coherent low probability is nothing but the normalized non-negative exact game. Okay, sorry. Next part, it's about counts of balance and exact game. Let me recall that polyhedral cone is a subset of Euclidean space specified by finitely many inequalities, namely homogeneous inequalities, where saying that scalar product of x with some vector I, normal vector, is non-negative. Further consideration concerns more dimensional Euclidean space R P of n. Elements of this space are vectors whose components are indexed by subsets of n. So therefore they are interpreted as set functions over n. So as I said, important classes of modulus in cooperative game theory are classes of balanced games and class of exact games. And they are an inclusion. Exact games are contained in balanced games. And inclusion is strict if we have more than 3 players. By the way, 2 other classes of games will be mentioned in the end of the talk. Okay, this page is to explain why this non-negative assumption on exact games is not restrictive. If you have polyhedral cone, by linearity space, it's meant the intersection of that space with -1 multiple of that cone. And it is well-known result in polyhedral geometry that every polyhedral cone can be somehow decomposed into its linearity space, and then some other space which is pointed, which means that it has extreme rays. Linearity space, both in case of balanced cone and exact cone, is a space of additive games, which are games of this form. This space has dimension cardinality of n. Okay, further fact from polyhedral geometry is that every polyhedral set actually has unique inclusion minimal linear inequality description. And description is by the so-called facet defining inequalities. To be precise, this holds for inequality description in its ambient space, which is in case of polyhedral set, the affine hull of that polyhedral set. And also another remark is the uniqueness of the inequality. It's up to its positive multiple. Why it is so? Because if we multiply a linear inequality by its positive multiple, so it delimits the same half space in that ambient space. Okay, additive games have this form. So for every event, it's sum of the components of some vector y. So this knowledge allows you to show that every exact game can be turned into a standardized exact game simply by adding a suitable additive game. This is called standardization in context of exact game theory. Point is that standardized exact game, it's then non-negative because it is super additive. And therefore, we come from original game to non-negative game, which we know that after standardization is the same like coherent lower probability. So this page is now to explain why the many inequality description for exact cone and for coherent lower probabilities are basically the same. They are equivalent. The previous observation implies that the facet defining inequalities for the exact cone and for the cone of standardized exact games are basically the same. Only difference is that in the latter case, you add this standardization constraints. Similar consideration can be done with the cone of non-negative exact games. In this case, you instead of equality constraint, you have non-negative constraint that the value for the singletons are non-negative. And that is already very close to coherent lower probabilities, which are normalized non-negative exact games. So also in this case, but in this case you have bounded polytope instead of the cone. So also the facet defining inequalities for the exact cone are the same like facet defining inequalities for the coherent lower probabilities. You just add two constraints, this normalization constraint, equality constraint, and this non-negativity constraint for singletons. Completely analogous consideration works for the cone of balance games and the corresponding class of low probabilities. These are low probabilities avoiding Schur loss. And also this works for other two classes of games, collision games I have not mentioned so far, namely so-called supermodular games and totally balanced games. An example. How the facet defining inequalities looks in case of 3 players. So in case of balanced games, we have 5 facet defining inequalities falling down into 3 permutational types. They are shown here. On the other hand, in the case of cone of exact games, you have 6 facet defining inequalities, and they fall into two permutational types only. Here, on this page, the inequalities are intentionally written in the way that one can possibly recognize their hidden combinatorial structure. In fact, they correspond to particular systems. To which system you can reveal if you look on the left-hand side of each inequality. But I will explain the details in a minute. Before that, I will bring you another example illustrating the situation in case of 3 players or sample space with 3 elements. So if we are interested in the polytope of normalized standardized exact games, so that polytope is actually a 3-dimensional polytope because here these 4 guys actually vanish. There must be 0 and this must be 1. So you have a reduction from 8-dimensional space to 3-dimensional space. And that polytope, this polytope of normalized standardized exact games, has 5 vertices, which are shown in this figure. Actually, it's a bipyramid. That means that it's a pyramid with whose base is this triangle. So you have one vertex here up and one vertex here on the other side. And you also see, if you see it geometrically, that this polytope, it's delimit by 6 inequalities, 6 facet-defining inequalities. Okay. I promised you to interpret these inequalities in case of the balance goal. So facet-defining inequalities were correct for this cone were characterized by Shapley in 1960s on basis of formal results by Bondareva. So they have kind of combinatorial interpretation because they correspond to so-called minimal balance collection of subsets of N, whose union is N. So in our example, when we have 3 players, these are these 3 types of inequalities. So for example, the first inequality, which corresponds to this super additivity inequality, corresponds to a set system corresponding containing 3 singletons A, B, and C, which, as you see, correspond to the left-hand side of that inequality. Analogously, this other super additivity inequality corresponds to another system which has 2 sets, the singleton A and BC. Again, this corresponds to left-hand side here. And finally, you have an inequality. This corresponds to the system of 2-element subsets of that basic set. Okay, I am going to formulate that result by Shapley in mathematical terms, but for this I need some concepts. So I need some definitions. So let N be again our finite basic set. That's I just recall, and P of N, it's notation for its power set. If you have a system of sets, that means subset of P of N, then this symbol will denote the union of sets in that system, and this symbol will denote intersection of sets in that system. We will also need some notation for incidence vectors of subsets of N coalitions. This is phi of S. This is a vector, this is 0, 1 vector, whose components are indicators whether the corresponding element of that basic set belongs to the set or not. Yes? Further necessary concept, it's a concept of constant vector. A vector whose components equal each other. This is a vector of this form. It's called a constant vector. A special case of it, it's so-called 0 vector whose components are zeros. Okay. Now we are ready for the definition of balance set system. So recall that any subset S of the power set of n will be called set system. So I first introduced the concept of non-trivial set system. Non-trivial set system on some set M, where M could be a subset of the basic set having at least 2 elements. It's simply non-empty system of subset of M, which does not contain the empty set and the set M. So it must contain some proper subset of M. By proper subset means it is a subset of n, but not empty. So that system will be called non-trivial throughout the talk. So balanced system on M is the non-trivial set system B, such that the incidence vector for M is a conic combination of incidence vectors for sets in the system B with all coefficients non-zero. Because we have a conic combination, this is simply another way of saying that the combination, it's a combination with all coefficients strictly positive. Okay, so that's a formal definition. And then we say that a minimal balance system, it's minimal if there is no balance system on the same set, M, which is strictly contained in B. And then we will call briefly, instead of saying minimal semi-balanced set system, we will say min-balanced system on M. An important fact which is sometimes omitted, but which is important from mathematical point of view, is that these incidence vectors of sets from the set system for the min-balanced systems are linearly independent. Actually, this is the characterization of the minimality. So let me illustrate it by means of an example. Again, have these 3 participants and consider the system of 2-element subsets of the basic set. Then it is a min-balance balance systems because of this conic combination. Where you express by this conic combination, you express the incidence vector for n. And also it is minimal because these vectors actually are linear independent. Okay, and here is the inequality assigned to such a min-balance set system. You take that uniquely determined decomposition of the incidence vector for n in terms of these incidence vectors for sets in the system. And because of linear independence, these coefficients are uniquely determined. But they are also strictly positive because we assume that system is imbalanced. So these are so-called balancing coefficients, as they were called by Shapley. And what is the corresponding inequality? It somehow corresponds to this vector decomposition. On the left-hand side, you have terms corresponds to sets in the system. Each set is represented by the corresponding value, and the coefficient is the corresponding balancing coefficients in that decomposition. On the right-hand side, you have the term for the grand collision, or for M, and the coefficient is 1. Okay. Example, again, 3 variables, three participants, and 2-element subsets of it. So this vector inequality then gives you this facet-defining inequality for the balance curve. Now, here is the result. Shapley-Mondeler theorem says the facet-defining inequalities for the cone or balance game are just the inequalities, these defined, which are assigned to min-balanced systems on the whole set of participants n. Okay. Before coming to exact games, let me add one more remark about another result in cooperative game theory from 1960s. And this is a result by Pelek, which is an iterative algorithm which is able to generate a complete list of all means balanced set systems on some given set of participants. The iterativeness in this sense means that you get a list of all min-balance systems over for 5 participants on basis of list of all min-balance systems over 4 participants. So as explained earlier, Shapley-Bondarva theorem gives linear inequality characterization of allowed properties avoiding Schur loss. And if we combine it properly with the result by Pelek, we are able, at least in theory, come with simple computational test of whether a given allowed probability avoids Schur loss or not. Okay. Let me come to the topic of exact game. And I will try to present it as a kind of analogy of the case of balance games. So as explained earlier, this result, characterization of facet-defining inequalities for this cone, actually gives you automatically a linear inequality characterization of coherent allowed probabilities. Basic step in this is the following concept. It's concept of semiconic combination. A linear combination of some vectors in Rn is called semiconic if at most one of its coefficients is strictly negative, which is written here. That means in case of, say, one vector, semiconic combination is the same like linear combination. But in case of, say, 2 vectors, semiconic combination, it's any linear combination with one exception, and that is combination with 2 negative coefficients. It's immediate from the definition that any conic combination is semiconic. But I would like to explain that the mathematical properties of the operator of semiconic closure are different than the properties of conic closure. By semiconic closure, I mean the collection of all semiconic combinations of vectors from a set. So for example, if you have 2-dimensional case, R2, and consider the positive quadrant, then the semiconic closure of this positive quadrant are 3 quadrants. They are 3 quadrants all except the negative quadrant. And if we take the semiconic closure of these 3 quadrants, then you got the whole space. So therefore, the operation of semiconic closure is not idempotent. Okay, and that concept of semiconic combination, its basic step to give the definition of semi-balanced set system. So here is the definition. Assume that N is a finite set with at least 2 elements. And we say that a non-trivial set system is semi-balanced if there exists a constant vector in Rn, which is a semiconic combination of incidence vectors of sets in the systems with all coefficients non-zero. You see the definition is nearly the same like the definition of balanced system on N. The only difference is that in case of definition of balanced system, you have not any constant vector, but you have constant vector whose all components are ones. Yes, incidence vectors of whole set N. And instead of semiconic combination, you have conic combination. So that's the only difference in these definitions. So therefore, in particular, every balanced system it's automatically semi-balanced. continue with the definition. A semi-balanced system will be called minimal if there is no another semi-balanced system on the same set N, which is strictly contained in that system S. And again, we will say, instead of saying minimal semi-balanced set system, we will say that system is min semi-balanced. Another remark, it's analogous to a remark we just already done with in context of balanced systems. In case of min semi-balanced system, the incidence vectors for sets in the system are affinely independent, which is weaker condition than linear independence. Let me recall that the collection of vectors is affinely independent if any combination, linear combination of those vectors, such that sum of coefficients is 0, must be necessarily combination with 0 coefficients. So it's weaker condition than linear independence of the vectors. There is some observations from polyhedral geometry showing that affine semiconic combination is actually implies that affine combination, if you express a vector as a combination of affinely independent vectors, affine combination, that expression is unique. The coefficients are unique. So this implied that any affine semiconic combination yielding constant vector, it's only one, it's unique. Let me recall that affine combination, it's a linear combination where sum of the coefficients is 1. Okay, as I said, clearly every balanced system is semi-balanced, but converse is not true, and examples are given on this page. By the way, also the union of two semi-balanced systems need not be semi-balanced, because unlike the case of balanced games, which are closed under union, these systems are not closed under union. So consider the case of 4 players, and this system S and T. S consists of singletons A and B and their union, and T consists of singleton C, then BC and ACD. So this vector inequality actually shows that this is semi-balanced. So this is a semiconic combination of the incidence vectors, and they give together 0 vector, which is constant vector. On the other side, in the case of this system T, we have another semiconic combination, but giving the constant vector of one's incidence vector of n. So this shows that both systems are semi-balanced, and actually they are minimal semi-balanced because these vectors are finally independent. By the way, their union is not semi-balanced, but I will not explain the details in this talk. And now we are ready to assign an inequality to every min semi-balanced set system. So consider such a system, and we know already that there is a unique affine semiconic combination of these incidence vectors giving a constant vector. So we take it, and the left-hand side again corresponds to sets in that systems. So we have the values for coalition in that systems, and the coefficients are the coefficient in this unique affine semiconic combination. That means on the left-hand side, you have all the coefficient non-negative with one possible exception. On the right-hand side, you have the ground collision, and the value here, it's the shared constant in that constant vector R. And I have added here additional term, dummy term. Actually, I have not commented it in context of balance games. Actually, that is basically this term is 0 because value for the empty coalition is 0. But I added here an artificial term, adding some artificial coefficient. And the coefficient is designed in such a way that if you consider the homogeneous form of this inequality, put all the terms on one side, then sum of the coefficients is 0. You will see the meaning of the steps in the end of the talk when I will return to this. So example, if S is many balance systems, then this inequality actually need not be the same like the formally assigned inequality to a main balance system. But it's multiple. So therefore, the inequalities are basically the same because they define the same half space. So example, consider these 3 sets, collection of 2-element subsets of the basic set. So then this inequality assigned to main semi-balanced system have values coefficients 1/3 here because that corresponds to this affine combination they sum to 1. While the inequality for the same system but interpreted as balanced system, it's here. Here you have another standardization or normalization condition, and the coefficient with the grand coalition it's 1. Okay, this is an analogy of Shapley-Bondera theorem for the case of exact games, but it is not a complete analog of this. The result says these inequalities we have just defined characterize the cone of exact games, but some of them might be superfluous. Okay, to give you some example of inequalities which are not superfluous, which are facet defining, consider again these 2 inequalities which have been mentioned a while ago. So this is the superadditivity inequality for A and B. Now observe that actually that inequality, it's nothing but a rearranged version of an inequality assigned to main semi-balanced system, namely to a system which contains that singletons A and B and their union AB. To see this, you just move this term on the other side, and will that become the coefficient -1, and that exactly is the inequality which corresponds to that system. In that case, the coefficients with the grand coalition will become r equal to 0, so it's not present there. Note in this context that actually that system S is nothing but the union of some mini-balanced system on M, which is set AB. You add to that set AB. Actually, that's a general phenomenon. Once you have a main balanced system on certain strict subset of the basic set, the grand coalition, you add that set to it, so you obtain a main semi-balanced system. So another facet defining inequality, which was mentioned earlier, is this, and you see it corresponds to this set system. Okay. Once you have more than 3 players, then surprisingly, those inequalities which corresponds to balanced systems on a whole set of players are superfluous. They are not needed. They are not facet defining. So therefore, the following concept makes sense. A semi-balanced set system which is not balanced is called purely semi-balanced. And in case of a purely semi-balanced system, we have a special terminology. There is some exceptional set for this system. So this definition is formally given for any non-trivial set system. Having such a system S, we say that T in that system is exceptional within that system. If there exists a linear combination of incidence vectors of sets in that system, yielding a constant vector, such that coefficient with T is strictly negative and all other coefficients are non-negative. That basically means that the system S contains contains semi-balanced system which containing T, and in that system T has negative coefficient. Situation is much more clear in case of minimal semi-balanced system, because then the exceptional set is unique. So every main semi-balanced system uniquely determines its exceptional set. Now, I am going to present you some diagrams representing these facet-defining inequalities for the exact column. To introduce those diagrams, I need some preparation, some explanation how these diagrams are obtained. An important fact here is that in case of main semi-balanced system, these coefficients in that unique affine semiconic combination yielding a constant vector are rational numbers. That has important consequences. That means that vector equality can be multiplied by a natural number, and so you get vector equality where the coefficients are integers, this alpha s. Of course, so is alpha n, this multiple of L times R. And you can make some additional changes. You artificial add zero vector, which is characteristic vector for the empty set. And you add artificial coefficient here, this alpha 0, which is basically designed in that way that sum of all the coefficients, if put on one side, it's 0. Here, on the left-hand side, you know, because it is a semi-balanced system, all the coefficients are non-negatives with one possible exception. So there could be one of this set which has negative coefficients. So what we do with that, we move it on the other side. So another vector equality where on both sides we have non-negative integers as coefficients. Yes, and this possible exception set is just put on the other side. Okay, and now the diagrams I am going to present actually is a kind of a representation of this vector equality. I will explain in words what's the meaning or how the diagram is constructed, and then I will show you an example on the next page. So diagram representing a set system has a form of a pair of two-dimensional arrays, and these arrays have as entries colorful boxes. And these arrays encode the sides of the above vector inequalities. So left array describes the left side of this equality, and right array the right-hand side. The rows of the arrays correspond to the players, elements of the basic set. And columns of those arrays corresponds to sets. So each set has a specific color, and the value of that coefficients in that is expressed by repeating columns of the same color. I will see in a minute. Moreover, we have certain agreement that the grand coalition has reserved the black color. If there is exceptional set, it's in gray, and empty set has no color, a blank column, or white color if you like. Okay, here is finally the example. We have 5 players, and this set system which has 5 sets, 5 collisions. This vector inequalities you easily verify actually solves that it is semi-balanced, because if you move this term to the other side with -3 coefficient, then you get a semiconic combination giving a constant vector. So therefore, this is semi-balanced system, and because these vectors are linearly independent, even linearly, so they are finally independent, this system is minimal. So you see the respective inequality, if you remember the way how it was constructed, it's here. And here you have the description of representation in the form of a diagram. So this left array corresponds to left-hand side of this inequality, and this corresponds to the right-hand side. You see even empty set is represented by a blank column. Now rows corresponds to the players, and columns corresponds to sets. For example, set AC has reserved yellow color, so it's represented by boxes in the respective entries. Analogously for BC. Set ABD, sorry, has blue color, and to express the value of the coefficients, you repeated this column twice. Analogously, value for this exceptional set AB is here in gray. Okay, so I hope it's clear how the diagram represents an inequality. Okay, but that's not all, because problem has not been solved. The observation that many balanced systems yield superfluous inequality has already been done, Lohmann and others, in 2012. They made quite big progress in that direction, and they also introduced some inequalities associated then with particular set systems, although their definition, their association set systems with inequality was slightly different than we did it here. I would say more complicated, more awkward. They also notice that even a purely main semi-balanced system can induce a superfluous inequality. So in our 2022 paper, we succeeded to characterize those systems which yield facet-defining inequalities. And the way to this is the appropriate concept of combinatorial decomposition of a main semi-balanced set system. That leads for a solution. So here is a formal definition of indecomposability or decomposability of such a system. Assume we have at least 3 players, and consider a main semi-balanced system S on that. And then we say that a subset of the ground collision, which is not in the system, and which is not empty set nor the ground collision, yields a decomposition of it if it is an exceptional set in the larger system S union E. That basically means that that larger system has as a subset semi-balanced system having E as an exceptional set. That allows you to show that the facet in the inequality assigned to that system S actually is not facet defining, because it can be written as a sum of 2 other inequalities. Okay, a purely main semi-balanced system will be called indecomposable if there's no decomposition of this form. The point is that this combinatorial concept of decomposition, it's testable by means of computer, by simple algorithm, and that has been done by Vašek. Details are omitted here. And here's our main result. If we have more than 3 players, then an inequality is facet defining for the cone of exact cone, for the cone of exact games, if and only if it is multiple of an inequality assigned to an indecomposable main semi-balanced system. Before coming to the catalog, showing you the path catalog, let me add 2 remarks about some hidden symmetry in the list of facet defining inequalities. Basic observation here, there is certain anti-dual transformation between games, formally defined here. Property of this transformation is that it maps exact games onto exact games. So it's self-transformation of the cone of exact games. That observation allows to show you that if some inequality is facet defining for this cone, then there is a certain conjugate inequality to it, which is also facet defining for that cone. How you obtain that conjugate inequality? One simply replies any set by its complement, and while the coefficients remain unchanged. To illustrate it, let me come back here to the case of 3 players. And consider there are 2 types of inequalities in this case. So consider, for example, this inequality. So what is the corresponding conjugate inequality to this? You keep the coefficients, but each set you replace by its complement. So this term for MC, it's replaced by MAB. And this term for ABC, it's replaced by the empty set. Yeah, you see now the meaning of the empty set. BC, it's replaced by A, and AC by B. So in this way, you get this inequality. But if you realize that empty set is actually 0, you remove this and get this inequality. But you don't see that duality or that conjugacy if you don't have this dummy term empty set. So that was the meaning of these empty sets used in our inequalities and also in our diagrams. Okay. Actually, the same holds for case of balanced cone in place of cone of exact games. On the level of set systems, it also means replacing a set by its complement, giving the so-called complementary system. And conjugate inequalities can easily be recognized also on basis of their pictorial diagram. Basically, the operation is that you change boxes into non-boxes and conversely. One more additional remark is here. There is certain one-to-many correspondence between mains balance systems B on N involving at least 3 sets and purely main semi-balanced systems. What is the operation? If you have a set in that system, you choose and fix it, and you replace it by its complement. And by this operation, you get a purely main semi-balanced system on N. Point is that every pure main semi-balanced systems can be obtained in that way. So therefore, main semi-balanced systems can be obtained on basis of min balanced systems. Okay. Since the criterion in decomposability can be easily implemented, there is a combinatorial way to obtain or enumerate all the facet defining inequalities of the cone of exact games once you know all main semi-balanced systems of that set. So this table shows you what are the numbers of these facet defining inequalities. We have already observed that in case of 3 players, you have 6 inequalities. In case of 5 players, you have 280 inequalities falling into 16 permutation classes. And this is a reference to our web catalog. And in that catalog, in that web page, inequalities are represented by our pictorial diagrams. So now I will try to go to that catalog and show you how it looks like. So this is the web page created by Vašek, containing a catalog of all permutational types of indecomposable min-set and set systems. So here on this homepage, it describes the way how meaning of the diagrams and how they are constructed. And if you go to the case of n equal to 3, you see these diagrams here. This is a diagram representing that superadditivity inequality that MAB is less or equal to MA plus MB. And the corresponding conjugate inequality is on the other side of that hyperlink. You see that's the inequality here. If we come to say 5, the case of 5 players, you get 280 these systems falling into 18 permutational type. And you see, so this is one of the systems, and on the other side of this hyperlink, there is its conjugate system. Okay, so I will finish with remarks on some alternative approaches or related result. An alternative way to describe a polyhedral cone instead of finding its facets is to enumerate extreme rays of its pointed version. Applying this in context of this non-negative exact game leads, unfortunately, to a super exponential growth of the number of these rays with increasing cardinality of n. And this was confirmed by independent computing done in context of imprecise probabilities made by Erik Kwageberg. I hope I expressed correctly his surname, and Gert de Koeman. So here they found out, for example, that for n equal to 5, there is more than 180 thousands of extreme rays, or maybe types of extreme rays. So therefore, it looks like that there is no chance to characterize exact games or coherent lower probabilities in these terms. Despite we devoted some research effort in this direction, together with Vašek, in our 2018 paper, we offered a criterion to recognize whether a given standardized exact game is extreme or not. I also promised to make some remarks on 2 other classes of games. One of them was what I call supermodular games. A game is a supermodular if it satisfies the supermodularity inequality. Nevertheless, traditional terminology game theory, they do not call it a supermodular game, but convex game for some historical reasons. This concept corresponds in the context of imprecise probabilities to a concept of two monotone Laur probability. And as you, in this paper by Enrique and Ignacio, they made, as I already mentioned, they made a nice transition between concepts in theory of game theory and the theory of imprecise probabilities. And so they mentioned also the relation of this class of convex games to two monotone Laur probabilities. Laur probabilities were also studied by Sebastian in this paper. By the way, facet inequalities for this cone of supermodel games are well known. They were, for example, characterized in this paper by Kulpes and others. So these are these inequalities. On the other hand, characterization of the extreme rays of the pointed version of this cone, it's difficult. And it's difficult for the same reason as the case of exact games. Despite we devoted some research effort to this, in our joint 2016 paper with Tomáš Krupa, we offered a criterion recognized whether a given standardized supermodel games is extreme or not. And the last page is devoted to so-called totally balanced game. A subgame of a game specified by a subset M of N, having at least two elements, is simply obtained by restricting the characteristic function to the power set of M. It is known, well known, that a subgame of a balanced game need not be balanced. So this leads to this concept of totally balanced game. It's a game which is balanced and every its subgame is balanced. This class of games, which I guess probably have not been studied in context on precise probabilities, I mean its counterparts have not been studied, was a topic of intensive study in game theory. So it is well known that exact games are contained in totally balanced games. And task of characterization of facets of this cone was also solved in our paper with Tomáš Krupa from 2019. Let me add one more remark about these two cones. The cone of exact game, it's known to be closed under this anti-dual transformation. This is not the case with the cone of totally balanced games. Therefore, it implies that cone of exact games actually it's contain not only in the cone of totally balanced games, but also in its image by the anti-dual transformation. So it's intersection of two cones. And we had in this paper, we had a kind of conjecture which is true for at most five variables, five players, that actually exact games can be characterized as an intersection of totally balanced cone and its anti-dual image. This conjecture has been disproved by Vašek. In case of 6 variables, is found a counterexample, and another result in our 2022 paper was a result giving counterexample to that conjecture. Okay, that's all from my side. So thank you for your attention.